Hello all. Very good evening to all. Thanks for joining this session. So it's already 6:05, so we can start. As I mentioned in the last class. So before starting, am I audible to you? Can anybody respond? Thank you. So yeah, as I mentioned in the last session, so today we will deal with the groundwater basics. So essentially, we will look into this. What is a porosity and what is the unsaturated zones, what are the different geological formations, and how we can calculate the hydraulic conductivity and hydraulic gradient and other terms. So this will be like I decided to make it as a two session. So today we will only touch upon the basics. Maybe in the next session we will go deep, like cone of depression, transmissivity, and other formulas. So current today's session will be more like a basic session. So you will enjoy this session. So I have incorporated some few plots to give the essence of the topic. So let's get started. Mhm. So kindly mute others, or kindly mute yourself. Okay. Okay. Can anybody respond? Like, are you able to see the slides here?
Yes, sir.
Thank you. So yeah. So this is a session 5. So okay. So in the previous session, we have seen the dimensionless numbers. So I've seen like all of you have attended that session except one guy, Nandan. So anyway, we'll move forward. Like all these videos will be available in the YouTube later. So after finishing the editing and other reviewing the videos. So don't worry. Okay. So let's see how this soil profile look like. Let's say if I Okay, so let's see how the soil profile. Like, let's say if I have taken any cross section in the of the soil, so it may typically have this kind of a structure. So these are the plants which will have a roots, and it will be extended till the root zone. So this particular zone is called a root zone, and and this depth we call as root zone depth. So this root zone depth is very useful in irrigation subject, like where we calculate this irrigation efficiency and other things. There we deal with only root zone depth. Yeah. Okay. So yeah, see, basically here we are dealing with the groundwater, and so what is the groundwater? So the groundwater is like the water available beneath the land surface. Maybe it can be in unsaturated zone or in the saturated zone. It does not matter. So we call the entire this water will be called as underground water, and the water available on the top of above the land surface we call as a surface water. Okay. So this is not only groundwater. This can be say as groundwater table, like groundwater table slash zone. Okay. Okay. So this underground has a two zones. One is the first one is the unsaturated zone. Another one is a saturated zone. See, in the unsaturated zone, there are three different zones. One is a soil zone, intermediate zone, and capillary zones. Okay. So in this is unsaturated. It means that suppose if we take a block of soil sample, it may have like this shapes and other things. It will have pores which are not completely filled with the water. Not completely filled with the water. So that particular zone we call as unsaturated zone, whereas the saturated, all the pores of the soil sample will be filled with the water, and here the surface tension force will be zero. Okay. So suppose this is a soil profile, vertical soil profile. Suppose if we further divide, like if you look at the another type of uh, geological formation here. Let's say here in this left side plot as shows the general picture. But suppose if we go more deep into the very critical, very more deep into this underground water, so we can look into this way. See here we can see one is confined aquifer, confined bed, unconfined aquifer. Okay, what are these unconfined, confined, and will be explained in the later sessions. So for a time sake, you just see what is this. Okay, so as we in the left side plot, we have shown that underground water has a two zones. One is unsaturated zone and the second saturated zone. So in unsaturated zones, it may have some water table. Like see, if the water table is available in this particular location, okay. So up to here it is unsaturated zone, and just below that we have the water table exist. And at the bottom of the water table, we have the solid. We can have either clay or a rock. So above it, they have a water table, and it has a atmospheric pressure. And this particular type of water formation can be called as aquifer, unconfined aquifer. So unconfined aquifer will have a atmospheric pressure. It means that the water table. Suppose if you insert a piezometer here. See, if you see here the one piezometer is inserted, or if you dig the well, the water level will show as similar to the neighboring wood. Whereas compared to this unconfined aquifer, if you do the look at the confined aquifer, which is below at the top bottom of this right figure. So this is a limestone, and there has some open hole, and this blue color. All this blue color shows the water available in the pores. Suppose and in the confined aquifer, the water will be in artesian pressure. It means that suppose if you dig a well or if you insert a piezometer, the water will be shoot up till it reaches to the atmospheric pressure. Okay. So these are the like if somebody asks what is the difference between unconfined aquifer and confined aquifer. So one way to say is the unconfined aquifer will have a atmospheric pressure and confined aquifer will have a artesian pressure. And another difference can be unconfined aquifer will have a free surface, whereas confined aquifer won't have any free surface. Okay, it will be confined means confined from both the sides, from bottom as well as the top. Okay, these are the introductory of the underground water. Okay, let's look at some important geological formation. These are very important, so you can expect this is for 1 mark in a gate. Okay, so there are four different type of geological formation. Wow, first one is aquifuse, second one is aquifer, third one is aquiclude, fourth one is aquitard. Let's see what are these. So aquifuse is a geological formation that is not porous or not permeable. Okay, there is absence of interconnected opening, so it cannot transmit a water. So suppose like let's say if I have a big boulder or rock, let's say a rock. Okay, suppose if you try to pour water from this water on this side, do you able to see water in this side? No, because this is a uh, it does not have any pores, and it is neither permeable. So it has a very strong geological formation. So this type of formations can be called as aquifers. So one example is a solid rocks. So it does not contain any pores, or suppose if there is a pores available, then only whatever the water you pour on top of its surface will be percolated downwards. Since this type of structures don't have any pores, it won't able to permit the water through it. So these type of formations are called the aquifers. Okay, so coming to the aquifer, this is of our interest. So aquifer is a saturated formation of earth material that not only stores the water but also yields in a sufficient quality. So when we say yield means, suppose if you dig a well and pump a water. So this, and you will, if you pump a water in this case, this particular geological formation will be able to supply water at required rate. Okay, so aquifer, it not only stores the water but it also yields. So if we, okay, So these aquifer transmit water relatively easily due to its high permeability. So sand and gravel are can be classified as a good active aquifers. Okay. So remember these examples. These examples can be asked in a match the following type of questions. So these are the very important four formations. Okay. Next one. Next one is aquiclude. Okay. This is a geological formation that is impermeable, which means that it does not allow, so note down, it does not allow the passage of water through it, but it has a it is highly porous, and so it contains large amount of water. Let's say you take a clay as example. Clay is a highly porous, and it has the ability to store the water, but clay does not allow the water to percolate through it. So these kind of structures are called as this kind of formation are called as aquiclude. So aquiclude is a geological formation that is impermeable, which means it does not allow the passage of water through it, but it is highly porous. So it can store the water, but it won't allow to percolate. Okay, the aquiclude is formed when the aquifer is overlaid by the confined bed of impervious material. So one example is a clay. Okay, the last one, which is aquitod. So this is similar to the aquifer. So this is a saturated formation. So it permits the water through it, but does not yield water in a sufficient quantity as much as aquifer does. Suppose if you take if you dig a well in some places, so where you will see, suppose if you dig some well in some places, initially the water level may be here, but as you pump the water level will degrade, it will further degrade. But even though after time, after delta t, the level if still will may remains here or may go little more. So in this case, the aquifer is that the formation is does not providing enough quantity of yield. So these type of structures are called as a geological aquitard. So in summary, in summary aquifer aquifer and aquitard both stores and allow percolation. Okay, so you remember in this way. So let's say aquiclude, example is clay. It stores, but no percolation. And the last one, aquifuse. So you remember fuse means nothing, no storage, no percolation. Okay, so I hope these are clear. So aquifer tard, fur tard stores, allows the water, but tard will gives a less yield, where fur will give the more yield. And aquiclude, it only stores but no percolation. Aquifuse, no storage, no percolation. Okay, the example of aquifuse is rock, the example of aquiclude is clay, the example of aquitard is sandy clay, and aquifer is sand or gravel. Okay, let's solve one question on the same thing. Okay, this came in gate 2003, very long back, SEA. So let's match the following. This is the geological formation, this is the example. So I'll give 1 minute time, so I'll expect you to answer for this question. So I'll go back to the screen. Yes. So did you see the question? Like, can you answer this question? Any guess? It can be wrong, but you can guess it. Like it's fine. Uh, Sanjay or Gurvinder or Likita,
Yes, sir.
you can just guess it. Like,
Equifier is solid rock. Equiclude is
let me draw so that it will be easy. Wait,
Acute is
Mm.
For its
sand.
sand.
Okay.
Yes.
So
Acutard is
Aquiclude is
okay.
clay.
Aquiclude is clay.
Aqui-
Tar.
tard.
Aquitard is sandy clay.
Okay.
Acupuge is
Fuse
solid
is
rock.
solid rock.
Very good. Because like fuse, I told no storage, no percolation. Tar will be storage, but less yield. Crude storage, no yield. For aquifer storage as well as good yield. Okay, this is a very important question. Like you can expect for 1 mark in either in an interview or in gate also. So I can particularly say this example. So when I attended for this MTech interview in IIT Guwahati long back in 2015. So they have asked the two questions from this topic. One is of this match the following. Another is from uh, contamination travel time. So that we'll solve today only. That question we'll solve today. So these are the two major and important questions you can expect in any interviews, MTech interviews, or any not only in GATE, any other competitive exams also. Okay. So you must remember this four. Okay. So let's move further.
Sir, actually, we got confusion in this. Any shortcut to remember what is what?
Okay. So okay. Fuse. No storage. I already told like no storage, no percolation. Like in this way you remember. Okay. Fuse, fluid, storage, no percolation. Sorry for my bad handwriting. And next is tard, storage, less yield. For storage, good yield. Maybe in this way may help. I never like I did not thought of any shortcut. Maybe in this way you can remember. See, in this type match the following questions. If you are confident about two options, you may able to score 95% correct. Suppose what options you may have. Let's say option one may be like A, like let's say aquifer, na? A2, B, aquifer clay, B1, C maybe 4, D maybe 3. In this way, like in this way you can get a multi 4 options. In this case maybe you can go with elimination option. Like if you like fuse is a easy to remember. Fuse is easy to remember. Fuse means like fuse nothing, like no, like you can remember in that way. Fuse electrical in electrical terms, like fuse no storage, no percolation. And aquifer is easy to remember. For if you know these two terms, the other and by elimination process you can reach to the good answer. I hope it will help. Just try, because I never tried in that way. Okay. Okay. Let's move to the next topic. So this is another important ratio that we calculate in, this is not only important in hydrology, even it is very important in the geotechnical engineering also. So there you will use Darcy's law and other things. So here also we'll just touch what is the porosity. So porosity is nothing but a ratio of voids to total volume of soil or a rock. Okay. So if you remember this three-phase diagram from geotechnical engineering, so you will have this. Let's see if I draw a three-phase diagram. Air, water, solids. So you remember this three-phase diagram, like it will have like some Vs, Vw, Va, and this is a total is Vt, total volume. Okay. Suppose if I divide this volume of solids, so volume of voids. So this is a solids, and this together we call as volume of voids. So if we divide this volume of voids with the total volume, that particular ratio is nothing but as a porosity. And what is the range of porosity? It is greater than 0 and can be equal and less than or equal to 1. So it is not equal. It is so because see if you calculate like sorry, it can be equal also. 0 less than or equal 0 less than or equal to 1. This is the range of porosity. Okay, you remember this. So maximum can be 1 and the minimum can be a 0. Okay, so this is the range of porosity. And what are the terms here? VT will be the total volume of soil or a rack sample, and VS will be the volume of solids. Here I have shown you, and VB will be the volume of voids. Okay, so but usually you will find an eta in a range of zero point 0.3 to zero point 0.6 in a regular scenario. But there are special cases where you will have more voids compared to the solids. So that is these are the exceptional case. But in a usual case, you will observe the eta in range of zero point 0.3 to zero point 0.6. Okay. So let's see the how it can look like. Let's say if I added a zero point 0.3 meter cube of water to the dry sand. So dry sand, I have taken the dry sand of volume 1 meter cube. So it means that 1 meter here, 1 meter here, and 1 meter here. So dry sand does not mean that it all the it has zero voids. So there are some voids inside this dry sand. Okay, if I added this water to it, so I'll get a saturated sand. Hopefully, let's say if I get I got a saturated sand. So how I can now, what is the porosity of this thing? Porosity will be volume of voids divided by volume of total volume. So it will be zero point 0.3 by 1.0. So what is the value? So zero point 0.3. This is a porosity. Okay. So in this case, can you anybody say how the phase diagram look like? So this in this case, only we'll have a two phase diagram. One is water, one is solids. Okay, so this will become two phase diagram because the soil is sand is fully saturated. Okay, I hope this is clear. Okay, let's move to this next two basic definitions. One is a specific yield, so it can depend denote with SY. Another is a specific retention, SR. Okay, so porosity is important in groundwater hydrology because it tells us maximum amount of water that sample can contain when it's saturated. So I have shown you, suppose like if the volume of voids is zero point 0.3 meter cube, so it is possible to hold this much amount of water inside the sample. Suppose if volume of void is only zero point 0.1 meter cube, then only zero point 0.1 meter cube of water can be can be contain can be supplied to the groundwater soil sample to become saturated. Okay, so this is a way, and because of this it is very important to us, because in irrigation we often need to saturate the soil. Suppose like by supplying the water to the field, suppose when the plants are reaching to the permanent wilting point, we need to supply water to the field such that the soil becomes saturated. In that case, we should know how much water we should supply to reach to reach the soil to be saturated. In these kind of situations, we should have a knowledge of porosity. Okay, so whatever the water we supply to the field does not always guarantee to infiltrate, so and does not always makes the soil saturated. In that case, we should calculate the total amount of water we required to make the soil saturated in irrigation planning. So that has a significance of this porosity. Okay, so and this is very important here in irrigation planning and geotechnical engineering. So now the hydrologist, what they did is that they divide the water which is stored in the ground into the part. So they divide into two parts. One is a specific yield part, another is a specific retention part. Okay, so what is a specific yield part? Specific yield tells that how much water is available for human use, and specific retention tells that how much water remain in the rock after drained by its gravity. Suppose if I have a so let's say I have a soil I'll have a soil sample like this, and I dig a well here. dig a well and I pump the water. I pump the water. Okay, and how much volume you can able to take it out from this aquifer, that can be called as specific yield. And whatever the amount of water left out, even after draining out the whole sample, that can be called as a specific retention. Okay, so if you look at the specific retention, and specific retention is proportionally to the pore size. Suppose if you go to the finer size like a clay or sand, there will be more specific retention compared to the specific yield. That's why when we talk about the geological formations, you see aquiclude does not percolate anything, but it has a storage, but it does not allow the water to percolate. Suppose if you go to the aquitard, what is aquitard? Aquitard has a storage and it percolates, but not the amount it we require. So that is because the surface retention is more. So aquitard will have a surface retention more compared to the aquifer. Sorry, aquifer surface retention will be small. Okay, so what is the relation between this SY and SR? So porosity is equal to sum of SY plus SR. Suppose let's say we have taken 1 meter cube sample as similar to the previous slide. Let's say it has a specific yield of 2 meter cube, point 2 meter cube, and a specific retention of 0.1 meter cube. If you do this sum, you will get a zero point 0.3 porosity similar to this thing. So it is nothing but like, so how we can define other way to what we can define is that SY is the ratio of volume of water drained under the effect of gravity to the total volume, and specific retention will be volume of water retained against the gravity to the total volume. So these are the two important terms, and these are the terms will be useful while calculating the transmissivity and other terms in the next session. So okay, so maybe these are very important basic definitions should be remembered. Let's solve one question. Let's say if a catchment area of 120 hectare, the water table is dropped by 5 meter. Let's say this is a ground level. This is a groundwater table. Okay, and maybe due to some pumping activity, the groundwater table dropped by 5 meter. Okay, maybe like somebody had digged a well. Okay, because of this 5 groundwater table decreased by a 5 meter compared to the relative level. Okay, now assume this particular geological formation has a porosity of 28%. It can be expressed as 0.28 also, and the specific retention as 0.09. So now our aim is to calculate the specific yield and change in the groundwater storage. So how much is the total groundwater out? How much is the change we observed in the groundwater? So this is our interest. So from the relation of porosity and specific yield, we can write this way: eta is equal to SY plus SR. So from this we can calculate SY as 0.9. So this is volume of water can be taken from 1 meter cube of soil sample. Okay, can be taken from 1 meter cube of soil sample. If I what I mean is that, see, if I have a 1 meter soil sample as I shown in the previous slide, like 1 meter here, 1 meter here, 1 meter here. If this is a total like a fully saturated soil sample, even though this is fully saturated, but I can only able to take 0.19 meter cube of water only. So that is a property of this formation. So this particular formation has a ability to give 0.9 meter cube of water from a 1 meter cube of some soil sample. In a similar manner, let's see if I so what this is an analogy. So let's say if we observe the 5 meter drop in the water table, So how much is change in a groundwater storage we observed? Let's say area will be, so here area what we consider is 1 meter by 1 meter. Let's say here our area is 120 hectare. Is it can be written as 120 into 10 power 4 meter square also. 1 hectare equal to 10 power 4 meter square. Okay, this you can remember. So these two will become volume of soil sample, and this is a specific yield SY. So this gives the how much is the volume of water drawn from the aquifer. Okay, that will be 120 into 5 into point, and that will be 114 hectare meter, nothing but 114 into 10 power 4 meter cube. So alternatively what we can write, so volume of water taken to the total volume of soil sample. Okay, so in this way we can get this value. So these are very intrinsic definitions to be remembered. So don't neglect these things, because these the clear idea about these definitions will help you to solve in the 2 marks questions in the later sections. Okay, so yeah, let's move to the next section. So this is a in this slide what we do is that we will see how we can calculate the hydraulic gradient of a groundwater movement. So let's say here I have shown one cartoon. It shows the unconfined aquifer. As I mentioned, unconfined aquifer will have a free surface. This is a free surface, and the in unconfined aquifer will have a atmospheric pressure. So it will have a atmospheric pressure. Okay. So it clearly observe this dash line shows the datum plane. So datum plane, or we can say mean sea level also for some cases. Okay. Okay. So as we know in fluid mechanics, what is the total head? Total head will be pressure head plus kinetic head plus datum head. Okay. So but in the case of groundwater, the kinetic can be neglected, because the velocity of the groundwater flow is very small. So when we calculate the v square by 2g, and even the v is smaller, if you do the square of it, and it will be even smaller. So in this case, that's why we neglect the pressure head. So total head in the groundwater will be only Z plus hp. So Z is a datum head, and hp is a pressure head. Okay, this is the thing you can even observe. So here elevation head is a Z, and pressure head is HP. Okay, so up to here it will be called as a total head. Similarly, so okay, these are the basic thing. Let's say this is an unconfined aquifer, and this dash hatch line shows the bottom of aquifer. So let's say suppose if I insert a two piezometer at a distance of 780 meters in unconfined aquifer. So and this well one is here and well two is here. So and these two wells are apart, is located at a 780-meter distance, and it is observed that from this top of the well, the water is situated at a depth of 15 meter, but in a well 2, the water is situated at 18 meter. Okay, and the top of well is at 98 meter altitude. This 98-meter altitude is with respect to the mean sea level. And similarly, at the top of well, the location and the height is altitude is 100 meters with respect to the datum plane. Now, my interest is to calculate hydraulic gradient. So hydraulic gradient is nothing but uh, how much is the head lost by the water as it flows by 1 meter along the flow direction. Okay, so here we can see the hydraulic gradient is the change in the head per unit per unit of distance in a given direction. So in our case, the groundwater movement is in direction. Suppose how much head is losing by the groundwater as it moves in this direction. Okay, as it moves in this direction. So how it can be calculated? So in this case what we need to do is that we need to first calculate the total head in a both wells. Okay, so always when we, even in the fluid mechanics, even in the geotechnical, even in the hydrology, we should always look at the total head. Even if you look at this open channel flow in the previous session 3, there we calculated the specific energy. What we did was that in specific energy, we assumed the channel bottom as a datum. With respect to the channel bottom, we estimated the total energy. In this case also, we need to take datum as a reference, and from here we need to calculate the total head. So altitude of well, how much? 100 meters. So 100 meters minus 15. So 100 meters minus 15 will give the, is will be 85 meters. So this is a, so from here to here it will be 85 meters. Similarly, here altitude is how much? 98 meters. 98 meters minus 18 meters. So that will be like 80 meters. So this will be level of groundwater from datum, from datum. Okay, now this is a head loss. So this head loss occurred in 780 meter, so it will be like divided by 780. So total will be 5 meter by 780 meter. So it does not have any unit, so it will be like 5 by 780. Okay, in this way we can calculate the hydraulic gradient. So why I have shown is that it will be helpful in solving the next question, which I am going to show. This that particular question came in 2021 set 1. So where they have given the some angle of the groundwater also, but we don't need to consider the angle and other things. In any fluid mechanics or hydrology, we should always deal with the total head. Okay, so the total head will be here Z plus HP. Okay, total head will be Z plus HP. Okay, yeah. So let's move, before solving the question. Let's see what one important point called Darcy's law. So I think most of you know what is the Darcy's law. So Darcy's law will be velocity into velocity directly proportional to the hydraulic gradient. Velocity proportional to hydraulic gradient, and where velocity to make it equal. So Darcy's has introduced this proportionality constant, that is nothing but coefficient of permeability or hydraulic conductivity, so many names are there, so don't get confused. Okay, so as we know, this is the final form of a Darcy's law. So Q equal to K is a hydraulic conductivity into area, cross sectional area, into dH by dl, nothing but head loss per a unit length. Okay, so this is, suppose if if our interest is to estimate the coefficient of permeability or hydraulic conductivity, we can reshuffle the terms. In this way you can get it has a units of meter per day. So meter per day or per day. So where Q is the quantity of water per unit time. Unit time can be a day or a hour or a minute. And K is the hydraulic conductivity, which has units of meter per day or meter per second, or what, according to the discharge units. A is the cross sectional area. Okay, cross sectional area. Here you can see in the bottom figure. Suppose this is, for example, I have shown you. So height is 1 meter and width is 1 meter. So cross sectional area will be, here A will be 1 meter by 1 meter. So it will be like 1 meter square. Okay, this is a cross sectional area, and this cross sectional area we should always take perpendicular to the flow direction. Okay, so but this is a flow direction, and perpendicular to the cross sectional area, should be 90 degrees. So whatever the cross sectional we should take, it should be proportional to the flow direction. Okay, and dH by dl is hydraulic gradient. So as I have shown, hydraulic gradient. Okay, so this is all fine. So as we know, Q equal to AV. This relation we know from the fluid mechanics. But here the V is average velocity from the whole cross section, which is like 1 meter by 1 meter whole cross section. But as we look more closer, in a soil sample, the water will flow in this form and as a streamlines. Okay, and the velocity here, velocity inside the pores, will be much different from this v, will be not equal to capital V, which is average velocity. Now suppose, let's say, if one wants to estimate the velocity inside the pores, so this is a relation to be estimated, and this Vs will be much higher compared to the V, because this is the average velocity na, over a big cross sectional area. But this is the velocity in between the pores. Okay, so since suppose, let's say, we say that the flow is steady state, in this given the flow is steady state, this vs will be much higher. Okay, so the computation of vs is necessary to understand the contamination transport and the solute transport and other things. We can see in next slides how why we have calculated the vs and other things. Okay, let's say this is a prism of unit aquifer, like let's say, which has a 1 meter height, 1 meter width. Now I have inserted two piezometer at a distance of dl, maybe 1 meter. And when we inserted two piezometer in this two at a two locations of the sample, we observed a head difference of 1 meter. Okay, suppose, let's say, calculate in this way: k into a into dh by dl. So here, what is how much is area? A equal to 1 meter by 1 meter. It's nothing but 1 meter square. Okay. So how much is a DH? DH is 1 meter. DL is also 1 meter. Now DH by DL is how much? 1 meter. 1 by 1 will be 1. And now Q will become K into 1 meter square into 1. This DH by DL has no unit, so it will be like whatever the units will have. It may have meter per day, so it will be K meter cube per day. So what is a major conclusion is that the discharge from a from an aquifer is proportional to the hydraulic conductivity. Hydraulic conductivity. Okay. Suppose if the soil is very dry, then the discharge into the soil from the soil sample will be much higher. As the soil becomes saturated, the discharge into the soil will be smaller, because the hydraulic conductivity will decrease. So in the previous session, one of the session, I have shown you the way a graph between the moisture content and the hydraulic conductivity. As the moisture content increases, the coefficient moisture content increases, the hydraulic conductivity decreases. Okay. Okay, let's solve this question. CE 2021 CE set 1. Okay, this is a no, question 24. So you see this, this is a very big question, but the solution is fairly simple. Okay, so the two reservoirs are connected through a homogeneous and isotropic aquifer having a hydraulic conductivity K of 24 meter per day. Okay, so the units can be meter per day or per second, or depends upon our usage, but maintain the uniformity in the units, and has an effective porosity of 0.3 as shown in the figure. So the groundwater flowing in the aquifer, this is aquifer, and this is aqueduct. It means that it can be clay, so it only stores the water, does not allow the percolation. Okay, groundwater, and it means that only one direction flow is happening. See, there is no lateral flow, and even the bottom also aquifuse. Fuse means no flow. Okay, so it means that only one direction flow is happening here. Suppose in case of aqueduct, if it is an aquifer, then there will be two directional flow, then that is a different scenario. But in this case, so the flow is limited to the one direction, because it is confined from the top and bottom with aqueduct and aquifuse. Aquifuse means a rock, so there is no pores to percolate, and aqueduct is there is a storage, but it does not allow the percolation. Okay, suppose if the water in the reservoir 1 is contaminated, let's say if there is a pollutant is inserted in this thing, polluted. is inside is dumped in reservoir 1, then how much time it will take to reach reservoir 2. So this is our interest. So what is the time the contaminated water reach to the reservoir will be. So here if you see the time asked in days, and it is specifically mentioned around up to the one decimal place. So you always read when there's a fill in the blanks, you must read what they have asked and how to compute. Okay, let's move to the solution. So what are the given data? Given data, hydraulic conductor is given as 25 meter per day, and porosity is 0.3, and the length. So here is the reservoir 1, and here is the reservoir 2, and it is the 2 kilometer. So if you clearly observe, there is a 10 degrees angle. So one make a mistake here, rather than the taking this direct flow direction length, one may take as a this length, this length. This is a 2 kilometer where the flow is happening, and this is like a 10 degrees. So one may compute this cell by using the distillation. That is not at all necessary, because the flow is traveling 2 kilometers. It's not only traveling the cross sectional um, this L distance, it is traveling 2 kilometer distance, the whole distance. So the delta L DL should be 2 kilometer, or 2000 meters. Okay, you keep that in mind. So K is given, eta is given, L is given, and this how much is this? This is 5 meter. So perpendicular distance can be assumed as 1 meter. But now in this case, it is not necessary. When we calculate the discharge, we may require the cross area details. But in our case, our aim is to calculate the time. Okay, here we'll deal with the velocities only. So okay, moving forward. So, suppose if I draw in this case, what is the difference in these two? Difference will be 30 meters by 10 meters, because these this 30 and 10, they both are represent shown with respect to the datum. As I've shown in the previous slide, we should always work with the total heads. Okay, work with the total heads. So here, if you see, this 30 meter has shown with respect to the datum, and here 10 meters also shown with respect to the datum. So now we can directly simply take what is the h of head difference, 30 meter by minus 10 meters. So it will be 20 meters. As we know, Q equal to A into V, and A can be taken out, and V equal to K into HF by L. So K is hydraulic conductivity. This is given as 25 meter per day, and HF is 20 meter, and length is 2000 meters. So by doing this calculation, we can get average velocity from cross sectional area A, that is 0.25 meter per day. But our interest is to calculate velocity in pores. Okay, which is nothing but Vs equal to V upon porosity, which is like 0.25 by 0.3. So it will be like 0.333 meter per day, which is much higher than the V. Okay, so as we know, velocity equal to distance by time. So we use the same distance by time. So velocity has no, distance we know, we can calculate the time. So by doing this, we can get 24,000 days. So this much is the time required. So to reach, suppose if you insert some pollutant or contamination, if you insert in this reservoir one, it will take 2400 days to reach. It's almost like more than nearly like a 10 years to reach to the reservoir through this particular aquifer. Okay. So this is the introduction for this groundwater hydrology. This is session 1. In the session 2, I'll introduce what is the transmissivity and other things. Okay. I hope